Hi everyone, I'm Yuli Niu from Nanyang Technological University. In this talk, I will introduce our work on overcoming the language bias in the real question answering task. In short, we propose a counterfactual inference framework for debiased real question answering. Real question answering is one of the most fundamental tasks in vision and language. In real question answering, machine is required to answer the question based on the given image. However, recent works have found that language provides a strong prior. For example, in the first version of VQA dataset, whose answer distribution is closer to the nature, answering tennis to the question starting with what sport is can achieve 41% of accuracy, and 2 is correct for 39% of the question starting with how many. As a result, the models that rely on the language prior have a poor out-of-distribution generalization ability when the training and test scenarios are quite different. Actually, the concept of counterfactual is not novel in real question answering. Recent works propose to generate counterfactual images or questions as the new triplets of image, question, and answer for data argumentation. In this way, these methods manually change the training priors and move towards unbiased training. However, our observations of the nature always contain bias. When you Google banana, most of the returned results are yellow. Therefore, it still remains an open question about how to conduct unbiased inference under biased training. In this work, we propose to imagine a counterfactual VQA scenarios to formulate the language bias. In the conventional VQA, machine hears the question, sees the image, and further extracts the multimodal knowledge from the inputs. We raise a counterfactual question. What would the answer be if machine hears the question but had not extracted the knowledge? In this case, machine can only make inference based on the language prior, which reflects the pure language effect. By comparing conventional VQA and counterfactual VQA, machine can conduct counterfactual reasoning and remove the language bias by reducing the pure language effect. To achieve this goal, we first establish the causal graph to analyze the causal relations in VQA. The impacts of question and image on answer can be divided into two parts. The direct paths reflect the single model alignment. For example, the pure language effects via the path from Q to A. The indirect path reflects the multimodal reasoning. Overall, we hope to exclude the direct effect of question from the whole. The causal effect reflects the comparison between two scenarios. The total effect reflects the causal effect in conventional VQA, where all the inputs are given or muted. The pure direct effect of question explicitly captures the language bias, where the effect of question through knowledge is blocked. From the cause-effect view, the language bias can be reduced by subtracting the pure language effect from total effect. Here we report the experimental results on VQA-CP and VQA benchmark datasets. VQA-CP is sensitive to language bias, where the training and test answer distributions are quite different or even reversed. In this out-of-distribution evaluation, our CVPR successfully overcomes language bias. VQA V2 is a balanced dataset where the training and test answer distributions are similar. Our CVPR can make a good trade-off between in-distribution and out-of-distribution evaluations and does not overcorrect the language bias. In comparison, LMH achieves high out-of-distribution performance with the sacrifice of in-distribution performance. In addition to reduce language bias, our CVPR can also preserve language context. For this example, CVPR recognizes the context large or small rather than answer yes or no based on is this. For the second example, CVPR tends to highlight category-related options rather than zero attributes. Thanks for watching.